All right, in chapter 15 so far, we've talked about how to find an antiderivative. If I give you the derivative function, you should be able to work it backwards and find me the original, the antiderivative. We also called that the indefinite integral. And just like when we talked about derivatives, and derivatives can be interpreted a couple of different ways. Remember, derivative is the same as the instantaneous rate of change, or the slope of a tangent line, or it's the velocity if I give you a position function. All different ideas that mean the same thing. We can find those answers taking the derivative. Well, an antiderivative can also be interpreted a couple different ways. In this section, 15.3, we're going to talk about how taking the antiderivative, or the integral, really is finding the area underneath the curve. So let me start off by looking at example number 1 with you. It says here to consider the region bounded by the y-axis, the x-axis, and the graph of the square root of 4 minus x squared. So we have the x-axis, we have the y-axis, and then we have this function that when you graph it, it kind of looks like this, right? And there's a certain area that's bounded by all those three things. And if we want to find the area underneath this curve, the problem is we might not have a shape that helps us figure out the exact area. It's not a perfect circle or triangle or square or rectangle. So what we might have to do when we have a curved shape and we want to find the area is, for right now, we might be able to only approximate the area, kind of give a close estimate of what the area is, but not an exact answer, by using shapes that we do have. For example, we can find the area or approximate the area using rectangles. And in this first one, we're going to do 2 rectangles. You might have noticed that we took this shape, this area underneath this curve, and we divided it into 2 rectangles using the left endpoint of these rectangles. So I knew that I was going to go from 0, and then the curve was going to stop at 2. And if I wanted to divide it into 2, then that means that each rectangle was going to be 1 wide. If I want to draw from the left endpoint, I'm going to take and I'm going to follow the left endpoint up to my function, and that's going to be where my height of my rectangle is. So in my next rectangle, if I know my rectangle is going to be here, then I'm going to start at the left side, I'm going to follow it up to my function and over, and that's going to be the height of my second rectangle. So I'm using the left endpoint of each rectangle so I can find the height. And if we want to use these 2 rectangles to approximate the area, then what we need to do is find the area of each of these rectangles and add them together. So I'm going to do base times height plus base times height. I have the area of the first rectangle plus the area of the second rectangle, and I'm going to add it together to approximate the area underneath the curve. You might notice, though, that the rectangles are way above my curve, and so the answer that I'm going to get is going to be too high. It's going to be what we call an overestimate. But that's all we can do for right now, is give an estimate. But let's try it. So now we need to figure out what the base and the height is for each of these rectangles. If I know that I'm starting at 0 and I'm ending at 2, that's a total of 2 units, right? And if I want to take those 2 units and divide it into 2 rectangles, well, 2 divided by 2 is 1. So I know that each rectangle is going to have a base that is 1 wide. Now I've got to figure out the height. Remember, the heights of these rectangles are this distance right here. And because we used left endpoints, I know that this is a y value when x is 0. So I can find this height by figuring out what my y value is when x is 0. That's going to be the height of my first rectangle, f of 0, whatever my y value is when x was 0. So what x value am I going to use to find the height of my second rectangle? Well, if my second rectangle was here, that was the height that we found. If I want to figure out this height, well, that's when x equals 1. So I can figure out the y value when x equals 1 to find the height of my second rectangle. So I'm going to find f of 1. That will give me my base times my height of the 2 different rectangles. When I take f of 0, that means I'm going to take my function, which, remember, was the square root of 4 minus x squared, and I'm going to plug in 0 for x so I can figure out what my height is at that point. When I did that, I ended up getting 2. I also, remember, want to find the height of my second rectangle. That was when x is 1. So I'm going to plug in 1 to my equation. 1 squared is 1. 4 minus 1 is 3. And I ended up with the square root of 3. So the base times the height of my first rectangle and the base times my height of my second rectangle. I ended up getting 2 plus the square root of 3. That's an exact answer. If I were to put this in my calculator, I ended up getting 3.732. That's approximately the area underneath the curve. Well, what this is really the area of these two rectangles. But we saw before that that was a little bit higher than what my curve was, right? My curve was down here, so it's going to be a little bit more than what the actual area is. So we know that this 3.732 is actually an overestimate. But we were able to use rectangles, 2 of them in this case, to approximate what the area is. So what if I took that same exact shape, the same exact function, on the same interval from 0 to 2, but instead of using left endpoints, we used right endpoints for our rectangles. So now I'm going to take my rectangles, and I know I'm starting at 0. I know that it's going to touch and end at 2. If I want to use 2 rectangles, I still know that each of these rectangles is going to be 1 wide. The base of each of these rectangles is still going to be 1. But now we've got to figure out what the heights are. And if I were to draw rectangles using their right endpoints, on this first one, I'm imagining the base of my rectangle being here. That means from the right end, I want to follow it up to my function and over so that the right endpoint touches my function. On my second rectangle, if my rectangle base is here, I want to go from the right side up to my function and follow it over. So you know, I have to sneeze. Excuse me. You might notice that the height actually doesn't go anywhere because it kind of gets stuck right there at the function. So there is a rectangle there. It's just nothing, right? It's just so squished that there's actually no height there. So really, here are my 2 rectangles, right? You can see clearly that the estimate that we're going to get when we find the area of these 2 rectangles is going to be an underestimate. Look at how much area is not accounted for underneath that curve. So this time our number is going to be too low. Last time it was too high. My rectangles were above. Now my rectangles are going to be too low. But we're just doing it and approximating the area. Let's do the base times the height of each of these rectangles. If I look at my first rectangle, I know that the base is going to be 1. The height is going to be this y value. Remember where it touches the function. So the height is the y value that corresponds when x is what? Well, when x is 1, right? When x is 1, I can find the y value to find the height of my first rectangle. So f of 1 would be the height of my first rectangle. What x value will help us find the height of my second rectangle? Remember, if this was the base of my second rectangle and I was using right endpoints, I know that the height is going to correspond to when x is 2. So I'm going to plug in a 2 for x and figure out what my height is. Remember that f of 1 means that I'm going to take 1 and I'm going to plug it back into my equation. F of 2 means I'm going to plug in 2 into my equation. So pause the video and tell me what you get for the heights of both of those rectangles. I ended up getting the square root of 3 and 0. And 0 should make sense. Remember this rectangle over here was so low that we didn't see anything? That's because it was squished and its height was 0. So that number should make sense. So now I have the base times height of the first rectangle, the base times height of my second rectangle. If I were to add those 2 areas together, I end up getting the square root of 3, or in my calculator 1.732. But remember, those rectangles were really low. There was a lot of space left over, so I know that this answer is actually too low. It's an underestimate. So 3.7 was too high, but 1.7 is too low. So what we can do is a couple of different strategies. If the left endpoint is too big and the right endpoint is too small, we can use what we call an average, or we can use what we call the trapezoidal rule, which is kind of the same idea. Another thing we can do is instead of using left endpoints or right endpoints, is using midpoints of the rectangle. So look at this picture. I have these 2 rectangles, the same base, both 1 wide, but instead of using the right endpoint or the left endpoint, I took from the middle and I followed that middle up, and then as soon as it hit the function, that's how I drew my rectangle. I took my next rectangle, I found the middle, I followed it up to the function, and that's where I drew his height. So now the heights are actually the middle of these rectangles, not the left or the right endpoint, but the middle point. We can still estimate, and this estimate is going to be a little bit better. There's a little bit above, there's a little bit below, but it's going to be better than just purely using left or right endpoints, right? So if I'm going to use my midpoint, let's do the base times the height of each of these rectangles. It looks like the base of this rectangle and the base of my second rectangle is still 1. But what x value is going to help us find the height of my first rectangle? Well, remember, the height of my first rectangle is now this point, which is what x value? Well, it's in between 0 and 1, isn't it? So can I say 1/2? The middle point between 0 and 1 is x equals 1/2. I can plug in 1/2 into my function to figure out the y value, or the height of my first rectangle. So what x value are you going to plug in to find the height of your second rectangle? Well, that's the point in between 1 and 2. So can we say 1.5 or 3/2? We should be able to plug those numbers into my function to find the height of each of those rectangles. So we could do base times height plus base times height. When I did that, and I squared 1/2, I got 1/4. When I squared 3/2, I got 9/4. I used my common denominators and added or subtracted my fractions together, and I got the square root of 15 over 4 plus the square root of 7 over 4. When I punched that in my calculator, I got 3.594, 3.3. Remember, this is not exact. This is still an approximate area, but it's better than what I had before. It's not as high as 3.7 when I use my left endpoints, and it's not as low as 1.7 when I use my right endpoints. So midpoint is going to give us a better estimate, but still just an estimate. So how can we get an even better estimate than using midpoints? Well, what if we increase the number of rectangles we used? Instead of just using 2 big fat rectangles, what if I used 4 smaller rectangles? You can see that's going to limit the amount of rectangle that's above or below, either way. And so it's going to give me a better approximation than just using 2. How could I get even better than that? Well, I could use 8, I could use 16, I could use the smaller and smaller and smaller rectangles until eventually all of the little spaces inside or underneath here is accounted for, and I'm finding the exact area underneath the curve. But we can't possibly do an infinite number of rectangles. We'd be sitting here all day doing base times height plus base times height plus base times height plus base times height plus base times height. We can't possibly do that for an infinite number of rectangles. So we'll talk about in the next video how we can do it if we want to find the exact. But let's finish this one real quick and do 4 rectangles and see how our estimation improves. Let's say we use 4 rectangles. And on this one, it looks like we're using left endpoints. If I go from 0 to 2, that's 2 units wide, right? If I go from 0 to 2, and that's 2 units total, if I want to divide them into 4 rectangles, doesn't that mean that each rectangle is a half wide? So the base on the first rectangle, the base on my second rectangle, the base on my third and my fourth rectangle are all 1/2, aren't they? And so if I have a base here that's the same, and a number here that's the same, and a number here that's the same, and a number here that's the same, if there's a 1/2 in each of these terms, can I really GCF out a 1/2? You can put it with each one if you'd like to, but I'm going to go ahead and GCF out a 1/2. From there, we still have to find the heights of all of these different rectangles. The height of my first rectangle looks like it's going up to the left endpoint and over, which corresponds to x equals 0, right? So I can find the y value when x is 0. Look at the second rectangle. The second rectangle looks like it follows up from the left. It touches the function and goes over. That's when x is 1/2. What would be the x value you'd use for your third rectangle? 1, right? And what would be the x that you're going to use for your last rectangle? It looks like 1.5, or 3/2. So now all we have to do is plug in each of these x values into our function so we can find the y value that corresponds, or the height that corresponds to each of these rectangles. I'm going to do that. I'm going to punch it in my calculator, and then don't forget to multiply each of those by the base, or 1/2, right? So I'm going to get my answer inside here, and then I'm going to multiply my answer by 1/2. That'll give me my base times height, plus base times height, plus base times height, plus base times height, my 4 rectangles added together. I ended up getting 3.259. That was really close to what we did when we actually did the midpoint formula, actually exactly. But the more we do this, the better our approximation is going to be. So instead of 2 rectangles, I could do 4. Instead of 4 rectangles, I can do 8. Instead of 8 rectangles, I can get a better approximation, I don't know, and do 100 little rectangles underneath that curve. The more rectangles I do, the better my approximation is going to be. But the only way that I can get an exact value for the area is doing an infinite number of rectangles. Let's talk about in the next video how we're going to do that.